record. All right, Organic Chemistry 2342, Summer Session 2, 2020. This week we're going to start chapter 16, which is aldehydes and ketones, and we're going to do some additional reactions we already learned from a previous chapter as far as the oxidations and reductions when we were talking about alcohols, reactions of alcohols and how to make them. We're going to continue on that discussion and talk specifically about the functional groups of aldehydes and ketones. But before we do, let's go ahead and do our administration for the beginning of this session here. We still only have about 25 people, so people are starting to chime in right now. So do this week. Of course, we have today's class. And again, look for that new Zoom meeting room each week so that we make sure we're all here together. Homework for chapter 16 and 17. 16 is aldehydes and ketones. 17 is the introduction to carboxylic acids. I'll have all of that up by 5 o'clock today so that you should start being able to do those. The aldehydes and ketones obviously first, and then carboxylic acids for that. We'll have our third group project. And yes, I have not uploaded the grades just yet. It turns out I ended up not working this weekend. I just felt too lazy. And so I will have all that up by 5 o'clock. And so we will have the grades for our number 2 group activity, our homework for last week, and our exam for last week as well. But our third group project will be this Thursday. And what I was going to do is for this is I was going to give you an exercise in nomenclature and priorities. Right now, we're introducing aldehydes and ketones. That is the highest priority group we've used so far. And then carboxylic acids are going to be that highest priority. What that means is that we're going to be naming it for those highest priority things. So we're going to go through a group exercise on Thursday to talk about priorities and how to use my prioritization table that will be updated on the Zoom, the track site as well as the Canvas site. Okay. So then we'll also have on Friday our third exam over chapters 16 and 17. It'll be on Top Hat at our 12 noon time, of course, as usual. I have changed the settings. There was a setting that got changed where it was recording audio for some reason, and that seemed to bog down a whole bunch of people and make it difficult for you to get in and stay logged in. So what I've done is I backed off that, and I've only made it so that you still have to kind of scan the room and then show your ID, but everything else should be like it was on the first exam. So that should really solve some of the issues we kind of had. We've had about 10 people have difficulty getting and staying in the exam, but I think I've solved those. So hopefully we'll see a much less stressful test on Friday. Okay. So again, this brings us up to about 28 participants now. And that is our administration for the week. Any questions on administration? And don't forget to sign up for those SI meetings. Daniel and I talked this morning about what we're going to do this week. And so I think we have a really good plan for some extra activities associated with the aldehydes and ketones and the carboxylic acids. So go chime into those when you can or when you're scheduled for those, and we can try to get some really cool stuff learned this week. Okay, so with that, I am going to start sharing my screen. Let me make sure I'm on the right. Yes, I'm on the right Wi-Fi. Perfect. I'm on the most stable Wi-Fi. So let's see if we can't share. Okay, so here we go, back at our shared screen with our aldehydes and ketones. Again, the fully, typed in part of these slides are on both tracks and Canvas. So if you want to go double check a spelling or double check a structure, those are available to you. And of course, then the ones we're filling in now, those will be found in the video that I'll post after class today. Okay. So moving right along, let me grab a stylus here. We're going to talk about aldehydes and ketones. And so this is another group. This is the first of a set of carboxylic acid, derivatives where we have a carbon-oxygen double bond, okay? Now we introduced that carbonyl group, that carbon-oxygen double bond, in a previous chapter where we talked about how it was a polar bond, it was sp2 hybridized, and it had a pi bond between the oxygen and the carbon. And that gave us some reactivity because the carbon was partially positive and the oxygen was partially negative. So what that's going to do for us is that's going to set the stage for these two new functional groups we're going to talk about, which are aldehydes and ketones. Okay. So the first thing I want to talk about is an aldehyde. An aldehyde has a carbonyl on it, but it only has one R group bonded to it and then a hydrogen bonded to it. So anytime you see the structure where you have a structure there, this is like a general R group here, where you have that carbonyl and that hydrogen there, that's an aldehyde, okay? And so it is halfway oxidized down to a carboxylic acid so that it has different reactivity. It's not as acidic and it has different reactivity, including it can be oxidized. Okay, so let's go and talk about the nomenclature of this. So with things like aldehydes and ketones, you're going to want to find the longest chain containing the carbonyl, okay, for both aldehydes and ketones. Most of the time, because you have a hydrogen at the end of the chain here, the carbonyl in an aldehyde will be at the end of a chain or on a side chain, okay? So what we'll do is we'll find that longest chain, and then we're going to drop the E at the end for an alkane and turn it into an Al. So it'd be an al. So for example, the simplest one we have here, that has one carbon in it, which makes it methane. So we'll have to drop the E and add Al. So it'd be methanal. Now, okay. Now, we have a common name for this one too. It's so common and used in industry, we actually call it something else. It's called formaldehyde. Aldehyde with a Y right here, formaldehyde. And we'll talk about that in a little bit when on the next couple slides. Okay, but let's go back to that systematic nomenclature rules right here. In this case here, we have a total of 2 carbons in the chain, which would give us an ethyl or an ethane chain, and we'll drop the E at the end and it would be ethanal. So any long chain you have, for example, this one right here has 1, you got to include the carbon in the carbonyl, 2, 3, 4, 5. So that would be pentanal. And we have a substituent on there. We're going to number always from the carbonyl as our number 1 carbon, which would make our substituent here on our number 5 carbon. So this particular one would be 5-chloro pentanal. Pentane, drop the E, add Al. So it'd be pentanal. Okay, so that is the systematic naming. In the aliphatic chains, if they're straight chains, if they're circular chains, what you're going to do is you're going to name the ring and just add the word carboxaldehyde. So in the case of this structure here, we have a cyclohexane. So it'd be cyclohexane carbaldehyde. And so you just tack the whole word onto the cyclic chain. Okay, now all other rules apply as far as if you have substituents, they have to be numbered lowest, they have to be alphabetical, et cetera, et cetera. Okay, so when you have substituents that are phenyl rings on a long chain, what we're going to do is we're going to name that for the longest chain. And in this case, our longest chain happens to be these 2 carbons here. And in those 2 carbons, we have we'll have ethanal right here. So we have a substituent on a carbon. Remember, we number from the carbonyl carbon. So this is our 1 carbon, which makes 2 carbon. So this structure would be 2-phenyl because the benzene ring acts as a substituent to the longest chain that it's named for. And then this would be ethanal. F-A-now, right here. Now, it's slightly different when the carboxylic acid, when the aldehyde is bonded directly to the phenyl ring. When it's bonded directly to the phenyl ring, we're going to say benzene carbaldehyde. So it'd be a benzene carbaldehyde. In this case here, where we have just our benzene, but it also has a common name. To shorten it a little bit, we call it benzaldehyde. Although it's not a special name like the case of an aniline or other benzene derivatives we talked about. We can name it either way, but the IUPAC name would be benzene carbaldehyde. D, that's an L, D, H, L, E, H, Y, D, E. Benzene carbaldehyde, all one word, no space, no dash. Okay? So, now in the case of multi-ring systems like this subset is called a naphthalene ring. So this would be just naphthalene carbaldehyde. Okay, so we're getting the idea that if the aldehyde is changing the name, we're going to have it, if a long chain is going to have an AL, but if it's a ring or a benzene, we're going to have to use the word carbaldehyde with it. Okay, so there are some common names you will need to remember. Okay, so there's three in particular that you'll need to remember, happen to be based on the names from their carboxylic acids. So in the case of the first one right here, if we were to take this and oxidize it further, it would turn into this compound here. And this is called formic acid. Okay. And we'll learn a little bit more about formic acid in the next chapter here. But the fact is this, when we have the dialdehyde of it, it's actually called formaldehyde. Okay, so we called it methanal on the previous slide. That's the IUPAC name. This is the common name, formaldehyde. Okay, now in the case of adding one carbon to the chain right here, that was ethanal because it has two carbons in the chain, but it's also named in its common name, named for its common acid, which is called acetic acid. So we call it acidaldehyde or acetaldehyde. Okay, and then that's why our common name happens to be this benzaldehyde, because that was benzoic acid, but when we've converted it to an aldehyde, the common name is benzaldehyde. Okay, and occasionally when we do this, we're actually going to use a weird naming system. If we're using a common name and it has a substituent, we'll use an alpha, beta, gamma substituent. And you'll see that in the homework, but we're not going to use it much in class. So don't worry about that too much. Okay, so that's naming aldehydes in both the IUPAC name, which is always right, and then the common names. These three common names in particular are going to be used quite a bit in just talking through class and in some of the reactions we're going to run. So make sure you know at least these three common names for aldehydes. Okay. So if there are no questions on aldehydes, let's go to the ketones. The major structure difference in the ketone is that an aldehyde has at least one hydrogen bonded to the carbonyl, okay? But the ketone has no hydrogens bonded to the carbonyl. It's bonded to two other carbons, okay? So that changes the way we have it. It doesn't always have to be at the end of the chain like the aldehyde does, because that hydrogen is terminating that chain. We can actually have it in the middle of the chain. So we have to find the longest continuous chain that contains the carbonyl carbon. It must contain this carbonyl carbon, or else it will not be the longest chain possible. Okay, so then just like with all other long straight chain hydrocarbons, we would drop the E at the end and add the word O-N-E or own to it. It's not one, it's own. So if we had 3 carbons, it would be propanone. If we had 10 carbons, it would be decanone. Okay, so, and again, we want to find the way to put that carbonyl at the lowest number. The lowest number possible is not 1, as in the aldehydes here. The lowest number possible is 2, because you have to have at least 1 carbon bond. So you typically see 2, 3, 4 in the ketone names. Okay. So let's talk about straight chains and how we would name them. Let's move over to blue ink here. We have a total of 1, 2, 3, 4 carbons here. So that would be butane. We drop the E in it, so it'd be butanone. Butanone. Okay, but we have to mark where that carbon is. Where that carbonyl is. And so numbering from this side, this would give us a 1 and a 2, 3 and 4. So 2 is our lowest number possible. So we have to put 2 butanone, okay? And in this case right here, we have 1, 2, 3, 4, 5 carbons. So that extends us up to pentane. So this would be 2 pentanone. Okay. Now, that's how you would name straight chains. If you're naming cyclic chains, what we'll end up doing is the carbonyl is always on the number 1 position, and then we'll name it for the number of carbons in the chain. So in the case of this compound here, we have 5 carbons in a ring, which would make it cyclopentane. So what we'll have to do is change it to cyclopentanone. Pentanone right here. And because the carbonyl is always on the 1 position in rings, we number from the lowest based on that. So in this case, it'd be 2-chlorocyclopentanone. Boy, I'm going to switch styluses. This is not right. Okay. So, and again, all the other rules of nomenclature apply. Okay, so now there comes a complication when we talk about having 2 different functional groups in the system if one is a double or triple bond, okay? Up to now, we assumed there were no double bonds in the system, and so we dropped the E at the end and add our own or our al for our system. If we have an alkene in the system, the alkene is actually used as what we call an infix. An infix tells you the nature of the carbon-carbon bonds, and we'll talk about this a lot on Thursday when we do our activity, where the difference between a prefix, an infix, and a suffix. And so in this case here, when we have a double bond and a ketone or aldehyde in a system, we have to show that there's a double bond there by including the word ene, as in an alkene, in the word. So in the case of this compound here, down here in the middle, what we're going to end up with is the total, how many carbons we have, 1, 2, 3, 4, 5. So we have 5 carbons, so, but we have a double bond. So that means pentene has to be in the name somewhere, okay? So what we're going to do is we're going to make sure that name is in there by saying an ene-one. So the alkene is telling you that there's there's a double bond in there, but the one is telling you what the name of the compound is for. So it has this group here. So we have to do pentene-one, okay? And so the way we're gonna write that is, because we have both of those functional groups in there, we need to show where each of those functional groups are. And once again, because we're naming it for the ketone, the carbonyl is on the lowest carbon, and that lowest carbon is going to be numbered from this side. What color go? From this side here, because we're own is at the end, so that's going to be our 1 position. So we have penta for having 5 carbons, okay? But now we have to tell us where that alkene is. And so if we're labeling from here 1, 2, so that ketone is at the lowest number, That means we have 3, 4 is the first carbon in our double bond, which gives us a 4-ene, saying that we have a carbon-carbon double bond, and then labeling where the ketone is, 2-one. Okay. Again, we're going to get lots of practice on this on Thursday, but the idea is whenever you have a double bond or a triple bond, it does appear in the name. Even though you're naming it for the ketone, it will appear right before that part. Okay. So any questions on the systematic naming of ketones? Again, longest continuing chain containing the carbonyl group, drop the E at the end and add O and E. Cyclics, we add the one and the carbonyl is always 1. And if we have an alkene or alkyne, it must be in the system and you must label the first carbon of that alkene and where the carbonyl carbon is. Okay, now, just like in aldehydes where we have common names for them, we now also have common names for ketones. And these are ones you'll probably want to know because they are pretty commonly used. Okay, so the first way we talk about ketones and naming them common ways is to take the carbonyl group and figure out which alkyl group is on either side. So if we had, for example, the carbonyl in the middle here, and we had this group here, like this, we would have 2 carbons on one side of the carbonyl and 3 carbons on the other side of the carbonyl. So we would have an ethyl butyl ethyl propyl ketone. Sorry, we have 3 carbons here. Ethyl propyl ketone. And again, we name them in alphabetical order. So if we had something like, instead of that right there, if we had a methyl group on this side and an ethyl group on this side, we would call that ethyl methyl ketone. Okay, so it would just, you name either side of the carbonyl, and then the carbonyl itself takes on the name of ketone. Okay, it's unlike the common name where you include it in the name in the longest chain. Here you're naming each substituent bound to the carbonyl carbon. Okay. Now, there's a few really common ones that we really need to use because almost nobody uses the IUPAC names for them. And so the first common one is something that is used a lot as a solvent, and it has 2 methyl groups on here. The IUPAC name would be propanone because it has 1, 2, 3 carbons in the chain here, but it's commonly known as acetone. Avoid this. Stylus isn't like this. Let me try a different stylus here. C-E-T-O-N-E, acetone. Okay, so this is the one with just the 2 methyl groups on it, it's one of the things that can be either used in woodworking to clean off your materials before you glue them together, or occasionally it's used as a fingernail polish remover as well. Okay, the other common one we want to do, it has the acid name in it right here, is called acetophenone. And so as the name suggests, we have a CH3 group on it with that carbonyl there, but with the other side of it, it's actually going to be bound to a benzene ring. And so this is called acetophenone. A-C-E-Y. A-C-E-T-O-P-H-O-N-E-O. Acetophenone right there. And then the last common one is actually 2 benzene rings hooked together. by a carbonyl right here. So it'd be like a dibenzoketone right here. We call this benzophenone. Benzophenone for having two of these, and it's spelled B-E-Z, no, N-Z-O-P-H-E-N-O-N-E. Phenone, benzophenone. Okay, so those are the three most common ketones we'll need a common name for. We use them again and again in other reactions, making a lot of different alcohols and other carbonyl compounds. Okay, questions on nomenclature of aldehydes and or ketones. Very quiet today. I keep thinking I'm muted on here and nobody can hear me. Okay, so let's move on and talk about properties and how these are different from some of the other functional groups we talked about so far. So the first thing I want to talk about is the different types of bonding available to us from what we'd seen in other systems. So if we look at the boiling points of different materials, we're going to see that butane or all alkanes only have those van der Waals forces, those low dispersion forces. And so they have very low boiling points because that's an induced dipole interaction. Those are very weak interactions. When we got to alcohols, we found out that hydrogen can hydrogen bond to the lone pairs on adjacent oxygens to give us a big boost in the boiling point of the system because of that hydrogen bonding. Well, in the case of aldehydes and ketones, we do have an interesting interaction here because we have the partially positive carbon here and the partially negative oxygen here. We do have what we call a dipole. And that dipole can be attracted to another compound. For example, if there was a carbonyl here, the partially positive side of this carbonyl is attracted to the partially negative side of this oxygen, giving us that dipole-dipole interaction. Now, this interaction is not as strong as the hydrogen bonding we see in alcohols and carboxylic acids, so it does not affect the boiling point nearly as much. Okay, so if we look at these by looking at their molecular weights, are all about the same, so it's not molecular weight driven. The introduction of the aldehyde gains a significant boost in the boiling point. It goes up about 50 degrees, okay? And it goes at that 50 degrees because of that dipole-dipole interaction. Again, it's not hydrogen bonding. That's not an acidic hydrogen. It's a dipole-dipole interaction. We see the same thing with ketones here. And because the carbon here can donate a little more electron density to the carbonyl plus, it has a slightly greater effect, but it's a noticeably greater effect, giving us a slightly higher boiling point here. However, if we were to take that carbonyl away, not have that dipole-dipole interaction, just have that hydrogen bonding action, we're going to get the boiling point to jump another 50 degrees just by that hydrogen bonding interaction. So our hydrogen bonding is the strongest interaction we have so far. Our dipole-dipole is next, and then our van der Waals forces are the weakest forces we have. What that gives us is that most aldehydes and ketones tend to be freely soluble in organic solvents because of that dipole-dipole interaction or the long chains having a van der Waals interaction with the long chain alkanes. However, aldehydes and ketones of less than 5 carbons can be water soluble because of hydrogen bonding. Okay, and there's enough hydrogen bonding to get it to pull away and get it to interact with the water to get it to dissolve. But over 5 carbons, they tend to be insoluble in water because the nonpolar tail tends to take over. That nonpolar interaction with the alkyl chain tends to break apart what little hydrogen bonding you have, and it tends to become insoluble in water. Oops. Okay, So that being said, let's talk a little bit about the spectroscopy associated with these aldehydes and ketones. Okay, so let's remember where our spectroscopy, where we have the high end band here above 3000 tends to be small carbon hydrogen bonding right here. Then the mid band between 1500 and 2500 is our carbon oxygen double bonds, our carbon-carbon double bonds, and our carbon-nitrogen double bonds right here. And then below this, we tend to have our carbon-carbon single bonds, carbon-oxygen single bonds, etc. So when we look for aldehydes and ketones in this region, we're going to see a strong absorption peak in the around 1700 wave numbers, okay? And so what we'll see here is almost all aldehydes and ketones will have this very strong, very pronounced peak in that region here. And it shifts based on whether or not there's a hydrogen bonded to it or not. For example, aldehydes tend to be a little bit lower at 1700 wave numbers. I'm sorry, the 1720 to 1740 wave numbers, higher than ketones, because that hydrogen there will let it be seen. Okay, now all the other peaks here are just our carbon peaks. Now, and then these are our carbon hydrogen peaks here. So when we're oxidizing our alcohols down to our carbonyl compounds, what we're looking for is a disappearance in our OH peak, which would be up here, and a growing in of our carbonyl peak. So we can actually watch for functional group transformation in IR by having one group transition from here to here. And what we'll find out is if you react that carbonyl compound with something to make an alcohol, you're going to see this peak disappear and an OH grow in. So we're looking for that functional group transformation in the IR spectrum. Okay. We also see that as a greater effect if there is conjugation in the system. So if there's a double bond nearby, or if there's a benzene ring nearby, what we'll see is that wave numbers go down because the energy is going down because of the conjugation effect, okay? So if we look at a hybridized, delocalized hybrid, conjugate hybrid right here, we'll see that we can delocalize that partially positive charge in that allele carbon position over here, and therefore that lowers the energy necessary to do that absorption, and we actually see a shifting down of wave numbers, okay? So in the case of just cyclohexane here, we have around 1710 wave numbers, and that goes all the way down to 1685, just being in conjugation with that benzene ring. Let's take it away from that benzene ring and just add a single double bond in conjugation here. And when you get a shift from about 1715 down to 1685 as well. So just the addition of that double bond allows it to get to a lower wave number. Okay. So in the case of if the carbonyl is actually in a ring, okay, that means that there's a little bit of ring strain in there, and so we'll actually see it difference from it being in a straight chain versus being in a ring. So for example, this would count as a straight chain ketone because the ketone itself is not in a ring. And so it has a, right around 1700 wave numbers here. And then by making it into a ring, okay, so we haven't really changed the number of atoms we have. All we've done is taken that carbonyl and put it in a ring. It actually shifts up in wave numbers. And by making that ring smaller and smaller and smaller, we're increasing the strain, and that number is getting to higher and higher wave numbers. And it has everything to do with that being pulled tighter and tighter out of that sp2 hybridized 120 degrees. Okay, so for NMR, I'm not gonna do the mass spec. We'll talk about that in a little while. If we're going to talk about proton NMR, that hydrogen on the aldehyde here is even more de-shielded than that in a benzene ring. Benzene rings absorb, that proton absorbs between 6.5 and 8 ppms. We're going to see that hydrogen on the carbonyl shift much higher, above 9 to 10 in particular. Now, if we have a methyl group next to a carbonyl here, these hydrogens are also de-shielded by the carbonyl compound here, and they're shifted up from 0.9, where they would be ppm, all the way up to around 2 to 2.3 right here. Okay, so just that carbonyl is enough to de-shield those hydrogens adjacent to it. Now, if you go one more carbon over, that decreases the effect and it gets closer to a normal carbon hydrogen bond in the proton NMR. Okay. When we talk about carbon NMR, those carbons that are adjacent to the carbonyl carbon are shifted slightly higher than they would normally be. Normally it's in the 15 to 20 ppm range. They're shifted slightly higher to the 20 to 25, again, from the de-shielding of having that carbon. The carbonyl carbon takes some of that electron density away. However, the carbon itself is shifted way high, almost above 200 ppms. So both aldehydes and ketones, that carbonyl carbon will show up right around 200 ppms, which is shifted about 150 ppm from where you expect it to be in a regular straight chain alkane. Okay, and so one of the things, the only real thing that's different about aldehydes and ketones is that you cannot split through the carbonyl. So if you have something on one side of the carbonyl, it's independently split from something on the other side of the carbonyl. So in the case of this compound here, the hydrogen here cannot be split by the hydrogens way over here. So we see that it has a single peak right here. These two groups right here are also found as a single peak. They're being de-shielded by the benzene ring and the carbonyl. And then the benzene ring itself, because it has a monosubstitution, is slightly split here. But what we'll see is that there's a very, very, so we rarely see the splitting of these systems here. Okay, and in the carbonyls, again, the carbonyl of both aldehydes and ketones are shifted way high above where you would see them before. We have benzene rings between 100 and 150, and then all of our other hydrocarbons are going to be below that. Okay, so we're going to do a spectroscopic activity in our 4th week. So we'll go ahead and hit all of these different topics again when we do our spectroscopic group activity later. Okay, so that concludes my section 1, just how to name them, what they are, and a little bit about their spectroscopy. Any questions on that?
Did you say that the hydrogen on carbon A, like on the carbonyl group, is not going to be split from the hydrogens on carbon B?
They very rarely split. They're actually split in this particular case, but they rarely split.
Why is that so? Because I would think that they would be different, because HA is like bonded directly to the carbonyl carbon, but HB is like one carbon away.
Right. Yeah, I'm sorry, I misspoke. What I meant to say was, if you have ketones, so the hydrogen here and the hydrogen here, don't split each other because it's more than 3 carbons away. 1, 2, 3. 1 bond, 2 bonds, 3 bonds.
Oh.
So it's more than that 3rd bond away. For the aldehyde, it does split. I'm sorry. You are absolutely correct.
Oh, okay.
I misspoke on that one. When you have a ketone right here, the adjacent groups on a ketone do not split each other because that's the fourth bond over. So this hydrogen cannot split this one because it's 4 bonds right here. However, on an aldehyde, the aldehyde is 3 bonds away from this methyl group here. So they do split each other. Okay, so you are correct. I am sorry, I misspoke.
Oh, that's okay. But wait, on the ketone, it's 4 bonds away.
Right. Yeah,
They're both 2 bonds away from the carbonyl carbon, and that's why they're the same.
correct. And
Okay.
so in the case of the ketone here, we have the 1 bond to the carbon here, the 2nd bond here. So there would have to be a hydrogen bonded directly to this carbonyl to get it to split, to have that 3rd bond.
Hmm.
Okay, but we have it bonded to a carbon here and then another hydrogen. So in ketones, you do not split through the carbonyl. Okay, in aldehydes, you are 3 bonds away. And so these two right here are split once by this hydrogen plus these 2 hydrogens are the same. So that's going to give us a doublet, which is what we see here. And the aldehyde hydrogen, which is way above benzene right here, is split twice by the 2 hydrogens on the adjacent, there's 2 hydrogens on this adjacent carbon. Right here, there's 2 hydrogens here. So that means this aldehyde is its own peak plus split by this carbon, this hydrogen, and this hydrogen to give us our triplet. So this bond, this peak right here is our triplet. It's our aldehyde hydrogen being split by these 2 hydrogens. And then this right here is our methylene hydrogens being split once by the aldehyde hydrogen.
Okay, makes sense. Thank you.
But yeah, but you don't split a hydrogen adjacent to a ketone with the other side of the carbonyl.
Oh, okay.
Yeah. So because this is 4 bonds away, these are 3 bonds away. So the 3 bond rule still works.
Wait, so does it have to do with like them being odd and even?
No, remember, hydrogen splitting only works through 3 bonds. Beyond that, it's just too far electrically away, and we can't see it. So you only look at hydrogens within 3 bonds of each other split each other.
Okay, I see.
Yeah, the hydrogens that are 2 bonds away are the ones that are on the same carbon, and they can either be the same or different, depending on if it's a ring or not.
Okay. All right, thank you.
Okay. So let's see. That brings us up to our next set, which is the preparations of aldehydes and ketones. And so I think this would actually be a good place to break and go ahead and stop recording. Stop share and stop recording.